Hi, I'm Alistair, I'm a games designer, and in this video I'm going to teach you how to hack into a terminal console, enter a system override password and use that to disable a security door network. Not in real life, that would probably contravene YouTube's code of conduct, but instead as a puzzle that you might find in a futuristic escape room game. So if you're on a space station or in a secret lab or in some kind of spy setting, this is the kind of game that you might find there. Now behind me I've got an example security door, so let me show you how it works. The door has got a 12-volt maglock here secured into the frame, and on the other part of the door here I've got the iron bar that goes with it. If I close the door, the system is currently activated. That is secured shut, and you can see I've got red LED chaser lights going around the outside to show that the door is locked. Now let's say that at some point later on in the game players come across a security console. Now that might be a desktop PC or it might be a laptop like I've got in this case. And this is running an app that says security system online, enter override password below. So let's just try password. No, nothing that time. Nothing that time either. Now, because I was lacking in inspiration when I coded this, the password I've set is actually password. And when I enter the correct password, if you watch the door behind me, I get a little confirmation sound. The LED pattern changes to green, and I can now open the door. Now, anyone who's watching this who might be a games master, think about how do you reset this puzzle. If you simply type any incorrect password again, the door will reset, we've got the LEDs back to red, and the door is now locked again. So this puzzle is basically created in two halves, so I'll talk about them separately. The first half is the hardware that's actually based around the door itself, and that is centered around one of these. This is a Wemos D1 Mini board. It's very similar to an Arduino, and in fact if you're familiar with the Arduino IDE, you can use that to upload code to this board. You can monitor it with a serial monitor. Most of the same Arduino libraries will work on one of these as well. The reason why I've chosen to use this board rather than an Arduino Nano or Uno or something like that is because this board is based around the ESP8266 chip, which has got Wi-Fi built into it. And it's going to be that Wi-Fi chip which I'm going to use to communicate with the terminal console that's running on the PC. So that's why I've chosen this board. This is controlling a strip of NeoPixels, which again I've used in previous projects, so you're probably familiar with those. And it's also got a relay module. This is what is controlling the power to the 12-volt maglock. So another really nice thing about these chips, I mean you can see it's very, very small indeed, and the relay module actually pins a line like that, so you end up with this really compact little unit. And if I just supply 5 volts either through the micro USB connector there or on the 5-volt pin, I've got a standalone little unit which I can address over Wi-Fi, and that's going to control the behaviour of that door. Let me show you a wiring diagram of how that's all connected. So here's my D1 Mini, and it's got its relay module placed on top of it. So if I just move that out of the way for a moment, you can see here's the D1 Mini itself. This is the ESP8266 chip, and you can see it's got the little Wi-Fi symbol there. Now, if this were attached to a standalone relay module, what you'd expect to see is that a ground line, a 5-volt line, and also a signal line would have to run from the module to the processor chip here. Now, because of the way that this sits on top here though, you won't actually see those wires because their pins are wired directly through. So the signal line that controls the relay is actually directly connected to pin D1 on the module board. Now you can't see that, but just be aware that if you do use a relay module like this, then writing a low or a high signal to pin D1 is what's going to activate the relay module. So you probably don't want to use that for any other purposes. Okay, so the D1 Mini board itself and the relay module, and also this WS2812B light strip, commonly known as a NeoPixel light strip, they all run at 5 volts. So I've got a 5 volt power supply down here, and that has got its positive 5 volt line coming to the 5 volt input here. That's going to power the relay and also the D1 Mini module. And I've also got it coming up here to the plus 5 volt input on the strip. And I've got the negative line, or the ground line, coming in here to ground and to ground. Now, notice, however, though, I'm not connecting them directly to the NeoPixel strip. I've got this capacitor on the line here as well. So the negative leg of the capacitor, the one that has this stripe on it here, that's connected to the ground line quite close to where it meets the LED strip. And the positive line of the capacitor here, this other leg here without the marking on, that's the plus 5 volt line. So the point of this capacitor here, this is going to smooth out the power input into the LED strip. When you're using an LED strip like this that's got lots of LEDs on it, if you were to sort of activate them all at maximum brightness, you're actually going to draw a surprising amount of current. And the current draw that would place on the system might impact on the processor and things here. So the point of having a capacitor close by, this is a smoothing capacitor that's just going to be able to supply and smooth out the power to the LED strip in the situation that it sort of currently requires a large amount of current in a short space of time. So that's just best practice I'm showing you there. You'll probably find it will work without it, but it is normally best considered to have a capacitor there. Likewise, you'll notice that the data input line here on my LED strip, that's connected to pin D4, but I've got a resistor here in the way. So this is a 330 ohm resistor, but you could probably get away with any value between about 300 and 500 ohms. And that's just placed in line, in series with the data input strip. Again, this is best practice. You might find that your LED strip will work even if you were to connect the data in pin directly to a GPIO pin on your microprocessor, but you really should place a resistor in line with it there. It will make your LED strip function more reliably, possibly make it last longer as well. So that's just these little extra components here are just because I want to show you, the best way of doing these rather than just something that works. Okay, so that's all over on this side of what's going on. And then at the bottom here, we've got a 12 volt mag lock. That's what's securing the door. That has its own 12 volt DC supply. So this is unconnected to the circuit at the top that's all running at 5 volts. Here we've got 12 volts. And the negative line from the 12 volt supply, that's going straight to the mag lock. The positive 12 volt is going to the common terminal, the one in the middle of the relay board. And then the normally open terminal is coming out and connecting to the other side of the mag lock here. So what this means is that when no power is being supplied to the relay module, so if for any reason this power supply here failed, let's say, these two terminals here are not connected. That's why it says that they're normally open, because there's normally a gap between them. And no current is going to be able to flow through this circuit. That means that the mag lock will not receive any power and it will release. So this is, again, just in the interest of showing you sort of the best way of doing this. If for any reason this power here failed, wiring it like this to normally open and common will mean that the mag lock will just automatically release. Which, bearing in mind we're talking about locking a door that potentially could have someone stuck behind it, that is the safest way to do your wiring like here. And that's basically it. Now, If you don't have a D1 Mini, or if you want to use an Arduino or another microprocessor board instead, that's absolutely fine. You'd basically follow exactly the same system. So if I scroll over here, I've got an alternative layout. And as you can see, it's very similar. In this case, what I've done though is I've replaced the D1 Mini with an Arduino Uno, and this has got an Ethernet shield on top of it. It could also be a Wi-Fi shield, or you could use an ESP8266 or an ESP32. Any processor like that would work absolutely fine. So I've still got my LED strip up here with the capacitor and the resistor, and that's going to 5 volts here. 5 volt supply is also going to power the board itself. And here I've got my relay. Now, because this is no longer sitting neatly on the pins of the board, I'm actually having to explicitly wire in the ground, the 5 volt supply, and the signal line here. So in this case, I'm using A0 as the signal pin for the relay, and I'm using A1 as the data line for the LED strip. That would just require a small change in the code if you change those pins to something else. And then on this side, still exactly the same 12 volt supply, 12 volt maglock. So yeah, I'm using the D1 Mini simply because it's nice and neat, it's very small, it's very cheap, and it simplifies the wiring a tiny bit just because I don't have to worry about it. But you could really do this same project with almost any microprocessor board. Okay, so that's the hardware that's controlling the door. The other half of this puzzle is the hardware around the security terminal itself. So I'm using this old laptop. This is probably about 8 years old or something. It's running Windows 7. It's not a particularly powerful PC, and it doesn't need to be. You could also use an old desktop machine. The only requirements really from a hardware point of view are that it needs to share a network with the controller that's running at the door. So the easiest way to do that is if they both join the same local Wi-Fi network. But you could also have a wired connection, use an Ethernet connection here, and also you could, instead of having the Wemos D1 Mini, you could have an Arduino with an Ethernet shield there. And so you've got a wired connection between them. The reason for them sharing that same network is because they're going to communicate with each other using a protocol called MQTT. Now, I have talked about this in a previous video, and I used it as a way of monitoring different props in an escape room and being able to reset them or solve them remotely. But in this one, MQTT messages are actually integral to the solving of the puzzle itself. It's what's going to send the signal from the terminal console to the door to say either to change to a locked state or to change to an unlocked state. And to do that, we need one more piece of software, which is called an MQTT broker. Now, this can actually be running on the same device here as the security console app, or it can be running in another machine that's in your ER control room if you have one. So it doesn't really matter. This can either be acting as both a client and a server, or it can just be a client and you can have a server somewhere else. It depends how complex your kind of technology setup in your room is. But either way, we're going to be running a program called Mosquitto, which is a free MQTT broker. So let me show you how you set that up. Okay, so all the software I'm using in this project is freely available for download from the internet. And the first piece is Mosquitto itself, which you can download from mosquitto.org. So as it says on the page here, Mosquitto is made by the Eclipse Foundation. It's open source, and it's what's called an MQTT broker. So you can think of this as being like a server. This is something that runs on a computer attached to the network, and it directs messages between different devices. So much like a web server serves out web pages to different browsers that try to connect to it, an MQTT broker routes and directs different MQTT messages between different clients. And those clients can be anything from Arduinos, Raspberry Pis, Android tablets, PCs. That's what makes MQTT such a nice system to use, because it's very lightweight, it's very easy to implement on different systems and allow them to talk to each other. So in an escape room setting, it's perfect for making all your different technology props talk to each other. So you can download that by just going to the download tab here, grab the latest version for whatever platform you're running, whether it's Windows or Mac or Linux. And when you've downloaded it, there's two ways to run it. You can either run it as a Windows service if you're in Windows, so this will be something that runs every time you load your PC in the background and just continues running. You can also run it as a command line application. So if you open a command prompt, go to the directory where you installed it and just type Mosquitto. Now I'm going to put the -V switch on the end. This is verbose mode, so this is going to give me some extra information every time a client connects or something like that. So you can see there it's opened a listen socket on 1883, and it's using both the IP version 6 and version 4 protocols. So that's my Mosquitto broker running. That's on my server. And like I say, you can either use the same device that you're using as the terminal console itself. That could be your server. Or if you have a central control room that has a PC in it somewhere else, you could set that up to be your server as well. It doesn't really matter so long as it's on the same network as any clients you want to connect. So the next piece of software we then need the client libraries that are going to connect to that broker. So I'm using two. On the D1 Mini itself, or if you're using an Arduino as well, I'm using a library called PubSubClient. You can download that from GitHub by going to github.com/Nollery, which is Nick O'Leary, /PubSubClient. And you just want to go here and download the zip of the latest version of that. So that's the MQTT client library that will run on an Arduino. And then we also are going to download from a different GitHub repository. So this is Eclipse Paho MQTT M2MQTT. And this is a .NET MQTT library. So if you are writing a Windows application, or if in our case we're going to be writing a Unity application that could run on an iOS tablet or on an Android tablet or on a smartphone, something like that, this is the MQTT client library that can be used for that sort of development. So we've got Mosquitto itself, that's the broker, and then we've got two different MQTT client libraries depending on the sort of client that we're going to use to connect. Obviously I'll include all this in the download that comes with this anyway, but this is if you're sort of following along at home, you want to get the latest versions of those libraries, that's where you get them from. So here I've got the code project that's running on the Arduino, and I've separated out into two separate sketches. This may be something you're aware of, but if you're not, when you create an Arduino project, you normally have a single sketch file with a .ino extension, and that needs to be contained in a folder with the same name. So here my main sketch is called security door controller.ino, and it's in a folder called security door controller. But you can also have as many other sketch files with separate INO extensions all in that same folder, and they'll all be compiled together as part of your project. So if you've got sort of a slightly more complicated set of code that's going on and it makes sense to partition it into separate sketch files, you can do that. And that's what I've done here. So I've got a separate file called mqttwifi.ino in the same directory. And in here I've placed all of the code that's to do with connecting to the Wi-Fi and connecting to the MQTT broker. And then here I've got my main sketch file, which has got my setup and my loop functions and stuff that's actually related to the game logic itself. I don't think anything that is here is new compared to something that I've used in other projects. So I did a whole video on MQTT in the past if you want to go back and check through my previous videos, but I'll quickly scan through it here. So I'm including both the ESP8266 Wi-Fi library and also the PubSubClient library, which I just showed. So that's for connecting to a Wi-Fi network, and that's for connecting to an MQTT broker. We define the name of the Wi-Fi network we want to join and the password, and we also define the IP address of the machine on that network that's going to be running the MQTT broker. So in my case, this is my server. If you're running your MQTT broker on the same machine that you're running that terminal application on, it will be the IP address of that. And I recommend you set up a fixed IP address on your router rather than a dynamic IP address, otherwise this will move around every time you run the sketch. Now, this is an important thing. So every sketch I've got running on my local network, I've given a unique device ID to, and this is just a fairly simple character string. And the reason for that is that the way that an MQTT broker works is it's sort of an ad hoc messaging network. It can have any number of topics, and they can be defined by any client that publishes to the broker. So you don't need to have those predefined in advance by the broker. Any client can say, hey, here's a message and it's related to this topic and I'm going to publish it. So the reason why I have every device have a unique device ID is because if a prop publishes a message that it only wants to be addressed to another device on the network, I use the device ID as the topic that that message is published in. So in this case, to activate the security door or to deactivate the security door, a client can publish a message to the topic called security door, and it will be a message with the content activate or deactivate. So whatever value you set here, make sure it's unique on your network and remember what it is, because we'll be using that in a bit when we start publishing messages. This is all fairly standard stuff, so we're just setting up an instance of the Wi-Fi client, an MQTT client that's using that Wi-Fi network, record the time that the last message was sent, and we'll create some buffers just to hold the message and also the topic name, and a pulse count, because we might want to send a heartbeat message and say how many pulses have been missed. So this is kind of to do with network reliability and things like that. But this is all fairly standard stuff here. This is the callback function that is called when a message is received in any topic that this device is listening to. So what we do is we copy the payload received, so that's the message, it's received as a byte array, and we'll copy it into our message buffer. We'll add a terminating character so that it looks like a string, and we'll just dump out a bit of debug information about what the message received was. And now this is where we define those two message keywords I was saying that we act upon. And you can add as many more cases as you want to this, or you can define different messages completely if you want to. But I'm using activate and deactivate because I think they're fairly sort of generic words that you could apply to a lot of different props. So let's say you want to adapt this prop, and rather than opening a door, you want to make a light flash on, or you want to turn a motor or activate a linear actuator, whatever. The words activate and deactivate would probably still have meaning in those different contexts. But like I say, you can call that whatever you want. So we'll compare the message received to activate, and if the result of a string comparison between those is 0, that's a kind of an odd way of writing it if you're not familiar with C program. But that says basically that there are no differences between the message received and the string activate. So in other words, they're the same. Then we'll call a function called onActivate. Alternatively, if there are no differences between the message received and the string deactivate, then we'll call the handler function onDeactivate. Okay? So, and like I say, you can set up more cases if you want, but that's the two we're defining here. Our Wi-Fi setup function, we'll just print out some debug information. We'll set the correct mode that we want to connect in. we begin a Wi-Fi connection with the ID and the password that were defined up here at the top of the file. So remember to set these, otherwise it won't work. And then here we just wait a little bit of time until the status of the Wi-Fi client says that it's connected. So here's just a little temporary timing loop just to wait for a bit while it's connected. And then when it has been connected, we'll just print the IP address that was assigned to this device to the serial connection. The MQTT setup, well, that's actually pretty straightforward. We simply set the server on the MQTT client object to the IP address. Again, that was defined at the top of the file. That was this bit here. And the standard port that MQTT uses for all communications is 1883. So I'm just using the default port there. That's what Eclipse is going to be listening on if you haven't changed any other settings as well. And we'll just assign that callback function we were looking at a second ago. And now finally we have a loop here. So this is the MQTT loop, which you can kind of think as like a sub loop that's going to get contained within our main program loop. So every time the sketch runs, in every iteration of the loop, we'll call this as well. If the client has become disconnected for any reason, or if it's not been connected yet, so that's what the exclamation mark there is, that means the opposite. So while the MQTT client is not connected, we'll just say, okay, well, let's attempt to connect to the broker. And we call the connect function. We pass in the device ID. So this is like sending a message to the broker saying, hey, I am device ID, I'm security door, and I'd like to connect to your broker, please. If that's successful, great, we've been connected. And then what we then want to do is we'll publish a message to the host device to say we've connected okay. So that's what this bit here does. We'll just smprintf is going to move this string here into the topic buffer, and here we're going to move the word connect into the message buffer, and then we're going to publish that message into that topic. So we're going to send a message to the host from this device ID, and then we are going to say that we have connected from this device, and that will, when we're monitoring the MQTT broker at the other end, we'll see that message appear just to say, okay, a new device has come online and has registered with the broker. And then on these lines here, so this was a publish message. Here we've got two subscribe messages. So this one here, this is going to subscribe to messages that are only meant for this particular device. So this line here, we're going to take to device, and then we've just got a little string placeholder here, and we're going to insert into that placeholder this device ID. So any other devices on the network that are connected to this MQTT broker, if they publish any message to the topic that's called to device / and then the name of this device, which was security door up here, we're going to listen for those messages. That's the first one we're going to subscribe to. And we're also going to subscribe to this one, which is to device / all. So this is when anyone wants to publish a message that gets sent to every device on the network, not just this one up here, but in fact to everything. So for example, at the end of the day, if you wanted to shut everything down, or if you had sort of a maintenance job and you wanted to dump some debug information or to reset every device, a client on the MQTT broker could publish a reset message to this topic and every device would receive that, whereas this one is only for messages intended for this device. If that all failed, that means that we're still not connected to the broker. We tried to connect and we failed, so we'll put out some error messages. We'll put the state of the client in there. We'll wait 5 seconds and then we'll try again. And that is that's about it for that one. Oh, here is this. There is a little shortcut for the publish as well. So if we want to call the publish message, from another device. Here's just a little method to do that. So that's all the functions related to the Wi-Fi and the MQTT. Now let's actually have a look about the specific functionality related to this prop controller. So the idea being that this whole sketch here, you could copy and paste this into any device running on your network, because there's nothing here that's game specific or controller specific. It's just about controlling to the network, receiving messages and calling callbacks. So this is kind of a modular approach to writing your code. This one here, this is about the specific implementation. What happens to this device when it receives a message that says activate or deactivate or something like that? So what does happen? Well, we've got a debug message at the top. This is always how I start off, just to say when that is there, that will dump out some more information. And we'll say the number of LEDs which are on our NeoPixel strip. So you can chain loads and loads of NeoPixel strips together. I don't actually know if there is a hard limit eventually, but certainly you can have hundreds and hundreds of LEDs in a chain. But we'll say how many there are, partly because we're going to use a function that bounces an LED backwards and forwards in a sine wave later on. So we need to know how many LEDs there are in the sine wave before we return again. Here's a library that you can download from here. Again, I've used this before, and that's very helpful for defining chase patterns and other useful LED control functions as well. We'll define the relay pin. So this is the pin on either the D1 Mini board, or if you're using an Arduino, whichever pin is going to the signal pin on the relay. If you're using the same relay module as I am, that is D1. You can't change it because that is the way that the pins are aligned between the module and the device itself. So that's fixed at D1. If you've wired in an external relay, you can use any GPIO pin you want for that. We've got some globals here, so we have an array of RGB values. That's going to be the RGB of each LED on our LED strip, and we've got a little state to record what state the puzzle is in. So it's either locked or unlocked, and it's going to move between those states depending on whether it receives an MQTT message that says activate or deactivate. So in our setup function, this is what's called when the program first starts, or if it's ever reset. We'll set up the Wi-Fi. Remember that this function was defined in this file here. So Wi-Fi setup is our generic Wi-Fi setup function. We'll call it from here, but it's actually defined in this other file. Then we'll set up our MQTT connection. We'll initialize the pin that the relay is plugged into, and we'll also set it to high because that's our default state for the board. And we'll also initialize our array of LEDs. So I'm using WS2812B, so this is NeoPixels. I'm using a pin D4 as my data pin that's connected to the data in the LED strip. And this is the color order for that strip. So rather than RGB, which you might think is more common, this is actually GRB byte ordering. If you get that wrong, all that's going to happen is that instead of displaying the color red, you're going to get the color green appearing instead. It won't really do any harm, but it'll just mean your color calculations are all a bit off. So you might, if the colors look weird, you might want to try changing the byte ordering of your color value there. Now we get to our two callback functions. So these were the functions that were called from our other script here, based on the message that was received. So if activator was received, onActivate is run, and if the word deactivate was received as a message, onDeactivate was run, and they are here and here. So onActivate, we'll just send out some serial information. We'll set the relay pin to low, and we'll change the state of the device to unlocked. And deactivate is basically exactly the opposite. We'll set the relay pin to high, and then we'll set the state of the puzzle to locked again. Depending on which relay module you use, some relay modules are what's called active high, and some are active low. So it depends on which of the pins is connected to the common terminal. So whether the normally closed or normally open is connected to the common depends on whether the signal is high or low, and some relays are the opposite of each other. So if you find that your relay is behaving the opposite way and it's unlocked when it should be locked, you might just want to swap these two functions around, and that's all. And finally we get to the program loop, which is actually pretty straightforward. So this whole section here is about updating the LEDs. So first of all, we'll fade out whatever LEDs were being shown already. We'll fade them to black slightly. That's what creates that nice kind of fading sequence. Now, if the state of the puzzle is currently that the door is locked, what we're going to do is we're going to create, this is a function here that creates a sine curve, or picks a value on a sine distribution based on a certain number of beats per minute. So we've got 13 beats per minute. We're going to choose a value between 0 and the total number of LEDs, and we're then going to colour that LED with a hue of 0, a saturation of 255, and an intensity of 192. So what this basically says is, this is red. Make a red dot and move it backwards and forwards from the two ends of the LED strip in a sine pattern. And then alternative, the state of the door is unlocked. What we'll do is we'll call this same function again, but notice I've changed the tempo here. So instead of 13, we're now 6, so it's a slightly slower oscillating beat. And instead of being red hue, which is 0, we've now chosen 96, which is a green hue. So we've now got a slower moving green oscillating LED that's just going to go backwards and forwards, depending on whether the puzzle is currently locked or unlocked. All this does here, these functions here, all they do is actually update the values in this LEDs array, which is a kind of a locally held copy of the RGB values. We then need to call this function to actually push that array onto the LED strip itself. So always remember to call fastLED.show in your loop function, otherwise the changes we made here won't actually have any effect. And finally, so remember I said that MQTT loop was kind of a sub loop that was going to be called as part of loop on each frame, so we actually need to call it as well. This is the main loop, this is what Arduino is going to call automatically on each frame, and what we want it to do is to call our MQTT functions as part of that loop on every frame. And that's it. And this is the Unity project, which is what I use to create the app that's running on the PC. Now, there is a huge amount to know about Unity. It's a very powerful program. It can be used to make kind of AAA games on Xbox One and PlayStation 4 and lots of other things as well. So I'm only using a handful of the features. But if you are not familiar with Unity, I do encourage you to go and download it. You can get it for free for personal use, or if you're a commercial entity with, I think, under $100,000 turnover or something like that. But go to unity3d.com, you can download it and check it out, because it's a great program for creating not only games but kind of PC applications and user interfaces, as I'm doing here. So what I've got here, so if I look at the scene view is like how a director would direct the actors on a stage or something like that. My stage is very simple. I have got a canvas here, which you can also see outlined in the hierarchy. My canvas has got a single panel in it. That panel's got a background in it. That's what just creates these scan lines to make it look like an old-fashioned terminal. But you could add any elements you want into the canvas here. So you can add animations or logos, or really style this how you want to fit in with the theme of your game. There's another sub panel that's slightly inside the other one. You can see I've got a border of 20 on all the sides, so that's the equivalent of sort of creating my little margin so that the text doesn't go right up to the edge of the screen. And finally, inside that panel, I've got my text object. So this is where I'm going to actually write all of the text in the game. So that's it really for the active systems. I've got an event system. This is a Unity standard component that's just going to listen for inputs from the keyboard, mouse, or any other game devices. I've got a camera, which is obviously going to render it all, and then I have one object here called door system, and this has basically got all of the game logic attached to it in a script here called security door system. And you can see I've exposed a lot of parameters that you can set related to the game. You can actually set here in the editor. So this is where you would set the correct password that users have to enter. Like I say, I've got it password at the moment, but you can set that to anything you want. Is that case sensitive or not? And do you want to maybe only allow like a pin code input, like only a numeric input rather than a password? You want to be passcode? You can change the behavior with those two switches there. This is the message that's going to be printed on the screen when the password is correct, and this is the message when it is incorrect. This bit here, this is just to say what are we going to update on the screen, what object are we going to update on the screen with this text. And when I clicked that, you saw the TextMesh Pro object here flash up. So this is my text box that's in the center of the screen. This is where we define the MQTT settings. So very, very similar to on the Arduino, where we had that separate script that declared where the MQTT broker was and things like that. This is the equivalent for the Unity application. So we give it a unique ID. Remember that the D1 Mini or the Arduino, that was called security door, and this one is called security terminal. So I've preceded them with the same words so that we know they're really two halves of the same components, the same puzzle. One's the terminal and the other is the door that it controls. Here is the IP address of the MQTT broker that's going to send and receive the messages between the terminal and the door. And again, that's the standard MQTT port, so you can probably leave that alone. This is the topic that the terminal is going to publish a message to when a password has been entered. So remember, this is how I specified to send a message to an individual device. I'm using the format of toDevice and then a forward stroke and then the name of that device. That's going to be the topic which we'll publish a message to. And the two messages that we could publish there are activate or deactivate. So these match up with the code that we used in the Arduino ID just that I showed you. So these just match the same there. Now, if I show you the actual script that is doing something with all these variables then. So I have a single C# script, security door system. Now I am importing, this is that library. Do you remember I said that there was a M2MQTT library? So I've got that in my Unity project in the script section here, and then I'm also importing that into my own script so I can make use of it. So that's exactly the same as if you're familiar with Arduino, where you include a library at the top of your sketch and then you can use functions from it. This is exactly the same. I'm using an external library, and that's going to enable me to use those MQTT functions in my own script here. So it's really similar. Okay, so here we've got, right at the top of my class, these are all those settings which we just looked at in the editor. So we've got, I didn't mention the audio, there's a little audio sound effect that plays. Yeah, that was right at the top here. So there's an audio source object attached to here, and that audio source is going to play one of two different sound files. So it's either going to say, access granted, which is the happy little beeping sound, or access denied, which is a sad beeping sound. So those are at the top there. Then we have all those other settings that I just talked about. So what the correct password is, can it be case sensitive, does it only have to be numbers, all those things. What the message is if it's correct, what the message is if it's incorrect, what the text container is on the screen. Then we've got all the MQTT settings here, and then we have a couple of private settings here that are just for use in the code here. And rather like, again, the Arduino sketch, we've got a couple of different states that the sketch can be, that the app can be in. So it's either ready for input, it's processing input, there was an error with the input, or it's complete because the correct input has been entered. So start, this is very, very similar to setup in Arduino land. So this is run once when the app first loads up. And we create a new MQTT client using the specified IP address and port. And then we pass in the client ID. So remember, this was called security terminal. We'll connect to the MQTT broker using our ID of security terminal. Or if we can't do that, we'll fail and dump out an error message. We'll just get a reference to the audio source component. We're going to use that later on when we play our sound effects. So that doesn't actually do anything yet. It kind of just finds the audio source for later. And then our update function. So this is the Unity equivalent of the loop function in Arduino. So this runs over and over constantly while the app is running. So if the app is currently in the ready state, we'll loop through. So input.input string here, this captures any input that's been entered on the keyboard, for example. And so what this is going to do is going to loop over every character that has been pressed on the keyboard. We'll assign it to a char called C, and we'll loop over every one, and we'll just see what the last keyboard key that was typed was. So if it was backstroke B, that's the code for saying that backspace has been pressed. So if that's the case, what we want to do is we want to take off the last character from the input. So we'll say that input is now equal to a substring of input. We'll start at the beginning and we'll make it one less in length than it was before. So that's cutting off the last letter. Otherwise, if the last keyboard key typed was backstroke N or backstroke R, so that's carried return or new line, which basically means that enter or return was pressed. Now if that's the case, what we want to do is we want to compare the input that's been entered to the correct input. And that's what we're doing here. So if the input is equal to the correct input, exactly, or if we are not bothered whether it's case sensitive or not, we'll compare the lowercase version of the input to the lowercase version of the correct input. And if that is true, all that is true, then we'll start the process correct input coroutine. So that's like saying this is the handler function that says when the correct input's been entered. Otherwise, if the enter or return key has been pressed but the input's not correct, we're going to start the process incorrect input coroutine instead. And finally, this is the bit that actually allows us to enter new letters onto our input. So if we are allowing numeric input only, we need to check whether C is between 0 and 9. Otherwise, we'll allow any input, which is this half. And if that's the case, we'll just append whatever the latest key pressed was onto the end of our current input string. Then what we'll do is we'll update the display. So if the state is anything other than complete, if it's error or processing already, what we'll do is we'll put the prompt onto the screen, so whatever it displayed before the user started typing, little double arrows, then whatever the player input, then we'll put a new line, and then we'll put the response from the system on. Again, you can customize this to whatever you want, to get some kind of custom display here to sort of start it with your own. Otherwise, if the state is complete, we'll just blank out the text display completely. And now we get our two callback functions. So this is the correct input one, this is the incorrect input one, and they are really sort of very similar. They're just the opposites of each other, just as they were with the Arduino sketch. So I hope if you're not familiar with Unity, you can see that the syntax is a bit different, but I hope you can notice that the structure is really very, very similar. So what we're going to do, if the correct password has been entered, then this function is called. So what we'll do for the time being, we're going to set the state of the puzzle to be processing. This will mean that we will stop listening to new keyboard inputs for a while we process the last input. We'll say that response is the correct response, and then this is where we publish the message to the MQTT broker to say that the correct password has been entered. So we'll call this publish.method on the client object, We'll send it to the topic that we specified, so that was to-device / security door, and we'll send the correct message, so that was activate, and that will get sent to the broker for any devices to listen to and act upon when that's received. We'll also play the audio clip that we called success, so that can be a WAV file or an MP3 file, whatever, that you just drag into that slot there and play it. We'll wait a second, just to celebrate the fact that we've entered the correct password, and then what we'll do is we'll blank out the response and we'll reset to ready again. So this is just resetting the state of the device to how it was before the correct password was entered. And the incorrect input, like I say, is almost identical. So instead of setting the state of the puzzle to the state of processing, though, we'll set it to error to start with. We'll say that the response was incorrect. Play a failure sounder clip, so this is our sad WAV file or MP3 file. And again, we'll call the publish method on the client object, but this time we'll publish the incorrect message, so this was deactivate in our case, to the topic, which was going to the security door. We'll wait a second, clear out the responses, and then return to the ready state. And that is the end of the whole script file. So that controls all of the logic that is running on the PC application. So that was a lot of code to take in, and don't worry if you didn't quite get all of it, especially if you haven't used Unity before, or if you're not so familiar with the Arduino IDE. I will put all of the code available for download from my Patreon page, so you can download it from there. You can obviously study it at your will, and if you've got any questions or comments, then do let me know and I'll do my best to answer them. But there's just a few more things I want to show you. And the first one is about how you can actually monitor what communication is going on between the terminal and the door itself using Mosquitto. So I'm going to fire up Mosquitto on this device, which is my server here. So there's my Mosquitto window, and I'm going to launch the broker with the V extension, which is this verbose mode. It is going to enable us to see the contents of any messages that are sent through the broker between devices. Now I'm going to turn on the door controller, so I'm just going to plug that in. It's running the setup part of the sketch now, and you see as the device comes online, the door is activated, and we can see a whole bunch of stuff has come up onto that monitor window. So we've seen it subscribe to the to-device / security door topic, and also to the to-device all topic, and it's published a message saying that it is online and connected. Now if I start the Unity app on my laptop here, we should see a similar thing happen when this comes online. So it's just starting up. Here we go. So we've got a connection acknowledgement, that's a CONAC, to security terminal, which is here. So just by viewing that monitor window, if that was running in a server in a control room or something like that, you can actually see that the devices have both come online. And now if I enter just a nonsense password to start with, you'll see that the message, the incorrect message that was sent by this device via the broker to the door, and that's all being intercepted and viewed along the way by that monitor window. Another nonsense message. Now this time I'll send the correct message, so password. You can see the door's unlocked, but we've been able to monitor every stage of the puzzle, what's going on, by looking at that monitor window, so that's really useful. Now, the second thing I want to mention is that in almost all of the projects I've shown in the past on my YouTube channel, I've used Arduinos with fairly simple inputs, buttons, rotary knobs, and things like that that can't go wrong. The risk if you put a fully functioning laptop computer into an escape room, however, is that players will inevitably find a way to break it or make it go wrong or something like that. So for example, what's to stop players from simply pressing Alt-Tab on the keyboard and going back to the Windows desktop? Well, you don't really want that to happen. Fortunately, there's a couple of ways that you can do that. Windows has a built-in mode called Kiosk Mode, which is specifically designed for running those kind of applications. But actually, there's a much simpler way that you can do it, and that's by remapping any keys that you don't want players to use using a little application called Sharpkeys. Now, Sharpkeys you can download from GitHub again. So it's randyrants/Sharpkeys, and it is a tiny little Windows application. It looks like this, and what it lets you do is write to the Windows registry and remap keys to other keys. Now, you can use this for all sorts of functions. If you are using a keyboard where the Control and Alt keys are the wrong way round or something like that, you can swap them over. You can use them to remap all the letters to a different letter. But what you can also use, for example, is if there's a key you don't want to be used for a particular purpose, so we could find if you have special keys on your keyboard that are designed for controlling sound effects, media, things like that. Maybe you don't want the numlock keys to be used. Or in our case, we probably don't want things like the Windows key to be used, or maybe the Alt and Tab keys. You can basically make a list of every key you want to disable on the keyboard and map them to this one instead that says turn key off. And if we enter as many rules as we want, so probably for a program like this, we want to disable everything other than the alphanumeric keys, for example. So we could simply disable every key that we don't want players to press, turn them off, and then if you click write that to the registry, that will disable those keys completely. Now, one thing to note, this will make a permanent change to the registry until you delete the registry key that this is assigned to again. So if you load the Sharpkeys program, or if you go back to your registry editor and delete those keys again. So be very careful when you do this. Don't accidentally, for example, delete all the keys or remap them all to something crazy and then write that to the registry. You will find it very hard to log on to your system again the next time you use it. So what I recommend you do is finding a device, an old laptop or something that you want to use for this game, creating a user account on it, removing the password from that user account so that you don't have to enter anything to fire it up, and then add the security console terminal application into the startup menu of your start menu, so it automatically boots when the computer loads, and then use this program here to remove all of the keys that you don't want players to press, and that will basically create a completely locked down console application that will be very safe to put in an escape room, and players won't be able to do anything with it other than interact with the application you've designed. So there you go, that's how you can create a high-tech escape room puzzle in which players need to use some sort of security console in order to deactivate a door lock or something like that. Hopefully you can think of many ways that you could customize this. I mean, something very trivial is just adding some logos or changing the font on here to match a setting. Or rather than controlling a door lock here, you could use that relay on the Wemos D1 Mini to control any other sort of effect as well. So hopefully that's given you some ideas that you can use in your room. If you do end up using anything based on this puzzle, please do let me know. I always love to hear stories or see pictures of puzzles that people have created. I think it's brilliant. As always, I will put the code, the Arduino code, and also the Unity project and the wiring diagram I'll put over on my Patreon page, so do check over there, and I've also got the resources that go with all of the other projects I've created as well will be available there as well. If you have any other comments or suggestions, please write them below and I'll do my best to get back to you. And thank you very much for watching, and I'll see you next time. Cheers.